Welcome back to Applied Mathematics. In this video, I want to introduce you to function notation. This is another place where the language we're going to use is incredibly general, but that generality is what gives it most of its power. All right, so we start off with a formal definition, which tells us that a function is a rule which maps each element of one set, which we call the domain, to exactly one element of a second set, which we will call the range. And there are a number of different ways that you can define functions. Perhaps the most straightforward is simply in a table of values. Before we start, I'm going to introduce a little bit of notation here. You don't see this all the time when people are talking about functions, but you see it often enough that I wanted to at least mention it. So we're going to name our function f. And our function f is going to take letters and map them to colors. So the domain of the function is going to be a set containing some letters, and the range of the function is going to be a set containing some colors. We can define this function using a table of values. I'm going to call my domain elements x, and then my range elements, the result of applying the function to those x values, will be f of x. So let's say we have 5 colors that we want to be able to choose from. Blue, green, red, yellow, and black. And we just start picking letters based on the first letter. Well, B will map to blue, G will map to green, R will map to red, Y will map to yellow, and then we run into a problem. Because we've already defined B as mapping to the color blue, we can't reuse B as the value that will map to the color black. So we have to choose something else, maybe a K. So with this rule, we have defined a function. One of the things that will tend to happen with a function defined by a table, it usually is there for some purpose. All right, so we are working with a machine that is going to be dyeing or painting something, and we hit the key to tell it what color that we want our objects to be painted. And then we end up in a situation where people are getting very confused because they're hitting B for black when B is giving them blue and K is the variable assigned to black. So maybe in the future we want to change that, and we want to introduce a new variable in the domain. I'll call it U, so that U maps to blue and K maps to black. And at some point in the future, we'll get rid of that B maps to blue, but for right now, for the sake of backwards compatibility, we're not going to get rid of the old option just yet. We now have a situation where the same range value shows up more than once. Right? We have blue up here, and we have blue down here. And that's okay. The rules of functions say that we have to take each domain element and map it to exactly one range element. It doesn't say anything about how many different things can be mapped to the same range element. I don't have a fancy symbol or notation for the domain. I'm just going to write the domain is. And we said that the domain was a set. It's the set containing all of the possible input values for the function. In this case, that's B, G, R, Y, K, and U. It might be worth rearranging those, putting them in alphabetical order or something, but I don't really know. It depends entirely on what application you are trying to look for. And then the range of our function is all of the possible output values. In this case, that's blue, green, red, yellow, and black. Remember, a set never indicates the same element more than once, so even though blue does appear twice in our table defining the function, we only need to name it once when we're trying to describe the range. All right, that's all well and good, but it's not very mathematical. So the next thing that I want to look at is a more math-feeling function. It's no more or less of a function, it's no more or less of mathematics, but it's going to feel more mathematical. And that is the algebraic function. When we define an algebraic function, we're going to do so by naming the function. In this case, I'll use g of x. I've already used f of x in the last example, so just the next letter in the alphabet. And then I'm going to give some expression. So maybe g of x is equal to 2x squared plus 3x minus 5. The advantage of doing this is that now I have a name for it. So if I'm going to be doing a lot of work with the expression 2x squared plus 3x minus 5, and I don't want to have to say 2x squared plus 3x minus 5 every time I need to use 2x squared plus 3x minus 5 in a sentence, I now have a shorthand name. I can just call it g, the polynomial g, or g of x. And if we plug in x equals 5 to g of x, well, we can shorthand that notation as well, and I'll write it as g of 5. This condensed notation is telling us evaluate the expression represented by g of x when x is equal to 5. And we know how to do that. We know how to plug in a number for x. And we could use a calculator, or this one is simple enough I can just work through it by hand without any issue. Things can get a little bit messy sometimes because you don't actually have to plug in a numerical value. It might be that we want an algebraic value. We want to evaluate g of 2t plus 3. And it looks a lot more intimidating, but it's the exact same process. Take our x, replace it with the thing that we plugged in out there, so 2t plus 3. And now we have an expression to simplify instead of a numerical expression to evaluate, but we still can do that. It's not that difficult. I'll square the binomial. I'll distribute. And then I'll combine some like terms. We have a 24t and a 6t, which all told is 30t. We have an 18, we have a 9, and we have a minus 5, which all told is 22. So g of 2t plus 3 is 8t squared plus 30t plus 22. We put in something, we got out something. It satisfies the rules for working with a function. And that's really all there is to functions. It is a notational convention that lets us give a name to an algebraic expression. It lets us shorthand the instructions for evaluating an expression for a particular value of the variable. And it gives us that same shorthand for rewrite the expression replacing this variable with this other expression. All of these are tasks that we have done before. There's nothing new here. It's just entirely a matter of notation. There's all this extra weight that comes with a function, and we'll explore some of the other things that functions allow us to do a little bit later on. Right now, just learning the notation is tough enough. There are a couple of wrinkles that I do have to talk about, though. The first one is known as implicit domain. Implicit domain is a convention of mathematical notation. Mathematics doesn't have to work this way, but choosing this allows us to do the most work with the least writing. Very much like the order of operations agreement that you are very familiar with. Implicit domain tells us that unless we explicitly specify otherwise, the domain of an algebraic function is the set of all real numbers which can be substituted into the expression and produce a real valued output. In other words, the domain of a function is anything you can put in and actually get something out. The flip side of that is the excluded value. An excluded value is something that you try to put into an expression and nothing comes out. Finding excluded values is easier, and then the domain is just the set of all real numbers except the excluded values. Right? So what operations could we possibly do that will cause it so that a real number doesn't come out? There are two that you have seen before. If you divide by 0, that's a problem. If you have any number a and you try to divide by 0, that does not give you a real numbered answer. The other one is the square root of a negative. If n is a positive number, then opposite of n is a negative number, and trying to take the square root of a negative number gives you trouble. So, putting that into an example, if I have the function f of x equals 2 over x plus 5, then the excluded values are the things that cause the denominator to become 0. Or another way of saying that, the domain is the set of all x such that x plus 5 is not equal to 0. And inequalities are solved the same way that equalities are. We have the addition property. We can subtract 5 from both sides of the inequality, and we get that x is not equal to negative 5. That's the domain of this function. I guess to be technically correct, we should set that up as using set builder notation, the set of all x such that x is not equal to negative 5. I'm not that worried about the details of notation. I'm worried about recognizing that if you try to plug negative 5 in for x, bad things happen. Another example, g of x equals the square root of 3 minus 4x. 3 minus 4x is underneath a radical, underneath a square root. And if you try to put a negative number underneath a radical, bad things happen. So we know that in order to make this function actually work, we need to insist that the stuff under the square root, 3 minus 4x, is greater than or equal to 0. Right? If it's less than 0, that means it's negative, which means bad things. If it's not less than 0, that means it's greater than or equal to 0. And we know how to solve inequalities. We can subtract 3 from both sides of the inequality. We can divide both sides of the inequality by -4. And we'll remember that whenever you divide an inequality by a negative number, it changes the direction of the inequality symbol. And we get that our solution here, the domain of the function, is all values of x such that x is less than 3/4. And once again, if you want to write that in set builder notation, that is technically more correct. And if you really want to be fancy, you can write it in interval notation, which is even more correct. But if you just gave me that, I would be very happy. What is the domain of the function? The domain of the function is x is less than 3/4. And just as a quick alternative, I said when I introduced this idea of implicit domain that we could use implicit domain whenever the domain is not explicitly given to us. So here I have a different function. H of x is the square root of 3 minus 4x. And this is a different function from g of x, even though they both started with square root of 3 minus 4x. Because this function has the domain explicitly given. -5 is less than x is less than -1. And because of that, we know our limitations. Based on the work we did before, we know that whenever x is between -5 and -1, we can safely plug it into this expression and we will get a result out. There are other values that we could try to plug in and they would give us a result out. But we don't just have the expression anymore. We also have the constraint. So if I try to evaluate, say, h of 0, well, that does not exist, dne, or perhaps is undefined. The language there, again, there are technical details that I don't want to get into. H of 0, right? If I plug x equals 0 into this expression, I get out the square root of 3, which is a real number. But that is completely irrelevant because the domain tells me I can only put in numbers between -5 and -1. We have to obey all of the rules when we're given a function. That takes us to one of the most interesting things that we can do with function notation. Which is piecewise defined functions. In one sense, a piecewise defined function is exactly what it sounds like. It is a function that can be defined in pieces. And this is something that you come across all the time without thinking about it. If you want to cut out a piece of sheet metal that looks like this, well, you can define what that bit looks like, and then change to a different definition for what that bit looks like, and then change to a different definition for what that bit looks like, and you get these 3 stacking definitions that overall give you the shape of the piece that you're trying to cut out. That's literally what a piecewise defined function is designed to do. It also lets us get around all sorts of problematic spots. If we are trying to deal with a function that has a square root in it, and we don't want to deal with it being undefined when the stuff inside the square root goes negative, we can break that into a separate piece and give some different definition to allow the function to continue. Generally, we denote a piecewise defined function using a curly brace like this. So h of x is going to be defined as being equal to 0 if x is less than 1, and maybe 5 over x if x is greater than or equal to 1. Notice that second piece, 5 over x. We know that dividing by x is a problem when x is equal to 0. And the way that we have set this function up, when x is equal to 0, we don't go to the piece that is the problem. Right? If I want to evaluate f of 0, the first thing I do is I look over here. 0 is less than 1, it satisfies this component, so I use that as my evaluation guide. F of 0 is 0. If I want f of 1, I again first look over here. This is an interesting one because it falls right on the breaking point, but we were careful about that. The top bit is x is less than 1, and 1 is not less than 1. 1 is greater than or equal to 1, so we fall into this category, which tells us to use that bit. So we're going to plug in 5 over x, but we're going to replace x with the 1 that we have. And 5 over 1 is 5. Likewise, if I want to evaluate f of 5, looking at the right-hand side, 5 is greater than or equal to 1, so I'm going to use the 5 over x version of the function. I'm going to plug in that x is equal to 5, and 5 divided by 5 is equal to 1. When you stop and think about it, hopefully that process makes sense. It's not a complicated process. It's not a big, elaborate undertaking. There's nothing hidden here, but you do have to stop and think about it. And it is a little bit confusing because you kind of have to read right to left. Right? When I'm looking at my function and I find a value, I first come way over here to the right. I figure out what I'm doing, and then I move to the left to figure out how to do it. Right? So figure out which one I'm using, then use it. Moving from right to left, it's the opposite of how you want to read, which is one of the things that makes this notation a little bit confusing, but as soon as you're accustomed to it, it really isn't that bad. I think I have gone on long enough in this video, so I'll wrap up with that. Next time, I'll play around a little bit more with functions. We'll see some tools that we can use to analyze them further, and I'll see you in that video.